Alright, I'm back. So this originally started out as a talk about adding video support to DRI2, but probably this ends up making more sense to add to DRI3, but I think some of the same ideas apply. But anyways, maybe about a year back I had some proposals for adding a few messages to DRI2 protocol to support pushing YUV video buffers directly to the X server. Although at the time I hadn't yet ported all of our stuff, our video decoders and all of the GPU stuff over to the new DRM gem based architecture. So since that time I've finished porting everything over, have things working, so I figure it's kind of time to revisit some of the patches we have and try and get them upstream in some form. So in the talk it all says DRI2 video, but maybe this really just means, hey, we should add this stuff to DRI3. So background. Traditionally, way to render video in X is XV, which in the best case is based on X shared mem buffers, although this isn't necessarily terribly good for hardware video decode, particularly if your decoders have certain memory requirements that are not met by random shared mem buffers. For using hardware decoders, it would basically amount to having to do 2 mem copies, one out of the buffer that the decoder is using into shared mem, and then another from that into to whatever the GPU is using on the Xorg side. Instead, what VA API and, as far as I can tell, VDPAU tend to do is they just use plain DRI2. So they'll scale, color, convert blit on the client side into an RGB buffer and then do swap buffers. But in the common case, this ends up being 2 blits instead of 1. So if the window's not redirected, or if the window is redirected to something that's different than the drawable size, the swap buffers on the X side will turn into a blit instead of a flip or exchange on top of the scaling blit that you're already doing on the client process side. So just to pick some arbitrary numbers, if you're playing 1080p video on a window that's nearly 1280 by 1024, in the best case you're using half a gig a second of memory bandwidth just for video presentation. Whereas if you can push the YUV buffer directly to the X server and combine the scaling and color conversion in a single blit, you cut that basically in half. And especially for a smaller UMA system, cutting that out is like on a Panda board that translates to something like 5 FPS improvement, getting rid of that extra blit. So for little devices where you care about power, or devices where that extra blit is consuming system memory bandwidth, it's kind of a nice thing to be able to get rid of. And I will say, with Wayland, we can already do this. You can push YUV buffers directly to the compositor. But there's really no reason we shouldn't be able to do that with X as well. So the idea with DRI2 video is basically to combine some of the ideas of XV and DRI2. Basically, you have a gem buffer that the client decodes into, although in this case it's unscaled YUV instead of RGB. Behind gem in your driver, you can deal with whatever your memory requirements are. If some hardware needs contiguous memory, or if you need to use memory that's remapped into a special sort of GART type thing, you can deal with that. But unlike traditional DRI2, the buffer can be actually multiple buffers. You might have one buffer for Luma and one buffer for Chroma for planar formats. The buffer will be potentially the full size of the video, not the size of your window. It might even have extra garbage around the edges. So usually for most video formats, like pretty much I think anything but MPEG-2, you end up having reference frames that are larger than your actual video because you got to deal with macro blocks that move off the visible screen and then back on in future frames. So you end up with some so-called codec borders around the edges, and those need to be cropped out when you do your presentation, when you do, display the video. And also by pushing these buffers directly to the X server, then now the DDX driver can do things like say, oh, hey, this is full screen. I'm just going to switch to use overlay directly and take the GPU out of the picture. And we're not using this with VA API or VDPAU, but I think the same thing could be useful for a VA API or VDPAU implementation. So essentially what it amounts to, I added a new protocol message to get video buffers, which adds a width and height, because now the width and height of the buffer are disconnected from the drawable size potentially. The other thing is you can have a lot more than a couple attachment points. So normal DRI2, you've got front or fake front and your back buffer. For video, you might have 16 buffers or however many buffers depending on the number of reference frames you need in the stream. So I'd also added DRI2 swap buffers video, which is like normal swap buffers, but adds some cropping coordinates so that you can say, hey, this is the actual sub-part of the buffer that you should show. And that can be used to get rid of the codec edges. It can also be used for like region of interest stuff, like if you're showing HD video in in a 4:3 aspect ratio or things like that. I'd also added a get and set attribute, which I haven't really used for too much yet, but the idea was to give the client a way to say, hey, use this color space conversion matrix, because actually different codecs and different resolutions, you might actually have different color space conversion coefficients if you actually want to do the color space conversion properly. And then I'd added a get formats, basically a way to ask the X server, hey, what color formats do you support? And I kind of had, and that's based on a 4cc in the same way that the DRM KMS add FB2 is. I mean, there's some cases where we just invent 4cc values for RGB formats and so on and say, this is DRM's meaning of that 4cc value. The idea is, well, let's use the same. So let's not convert formats between different parts of user space and kernel. Let's just have a common way to represent them across the board. And then lastly, in DRI2 buffer, I added a couple extra fields for dealing with planar formats. So now at the end of the buffer, you have a extra names and an extra pitches field, which is, if you have more than one plane, it's just a way to tack on that extra information at the end. Sticking it at the end made it easier to keep backwards compatibility. And things that are potentially missing. I I didn't add any way of explicitly dealing with interlaced or stereo, because that quickly turns into a combinatorial mess. I mean, one option is invent special 4cc values. The other option is ignore it. The other thing is, and this goes away with DRI3, because when DRI2, the client or the X server process is allocating the buffers, the client has no way of saying, having any say in the issue. So if the client doesn't have a way of passing around multiple buffers and users, in the client process, then maybe you want a way to say, hey, give me a single buffer. But in DRI3 video, if the buffer allocation moves to the client, then that issue kind of goes away. Yep. Yeah. Moving the allocation back over to the client simplifies a lot of this and makes some of this be a non-issue. Actually, the last point, one way of dealing with interlace or subtitles or other like RGB overlay of the video would be just make it possible to transparently switch between, so you can fall back to doing the blit on the client side for cases that are not supported by the protocol. Currently, that's not possible because the DRI2 and the DRI2 video attachment points are potentially overlapping. But if you just switch to a scheme where you're allocating on the client side and saying, here, show this buffer, it's in this format, then that issue goes away. Yeah. And that's about it. So, yeah, it started with the idea of adding this to DRI2, but if we're going to have DRI3, I think it's easier and cleaner just to support this stuff off the bat with DRI3, and then, yeah.
Just so you know, DRI3 is really just a small change to DRI2, so I'm just getting the same.
So you're actually going to keep the same proto?
All the swap parameter stuff, all the stuff is useful. The only change is how you actually do the swap, how you name the buffer. I'm just going to add a couple of new requests to create, take the DNA buffer and do something swap.
So, okay.
So just like you added swap bit here,
Mm-hmm.
I'm just going to add a swap DNA buffer.
Okay. So, but if the swap DMA buff, if we throw in the provision for having actually multiple buffers and cropping coordinates and things like that, then bingo, we're done.
And the 4cc format.
Yeah. So, I guess we should call them, I don't know, DRM 4cc's or something, because we're just. Yeah, so you might want to keep the like a get formats message or expose it as a property that you can query or something. But
how many buffers are you planning to send out with the swap buffers?
it would be one logical buffer, but maybe multiple planes. So it's not swap buffer for time n and n plus 1 and so on, but for YUV, if you ignore interlace and stereo, you can have up to 3 planes. I think common hardware decoders use probably NV12, so it'd be two buffers.
Could we make that 6 to actually handle interlaced or even stereo?
Yeah, so that was kind of my thinking, is for stereo and interlace, just push more buffers and let them get combined on the.
Sounds good, yeah.
Probably we need some way in the swap DMA buff message to say, okay, it's interlace left, right, and so on. But
so after swapping, the client still needs to have the old buffers, right? To
yeah.
be able to read from. So does that conflict at all with what you guys were talking about? Because after
no, you just keep a reference. Essentially,
Okay.
well.
The nice thing about using a DMA buffer is the reference is passed with the file
Right. So,
Okay. Nobody else? Okay. Well, thank you very much, Rob.
all right.